Welcome to the debate. Today we're looking at a proposal that, well, it effectively argues that the ground beneath our feet is just too stupid to survive the 21st century. We're examining the Global Living Ground Mesh, a concept from Tedford Enterprises. And this isn't just, an upgrade to 5G or better traffic lights. It's a fundamental architectural shift, fusing physical infrastructure, artificial intelligence, and even quantum technology into a single nervous system for the planet.
It is. An audacious claim, to say the least. We're talking about embedding intelligence into concrete, dirt, the seabed. But the real question we have to wrestle with is the trade-off. It's always a trade-off between capability and complexity. Does combining a global mesh of billions of sensors with autonomous AI agents create this planetary brain that actually saves lives? Or are we building a system so incredibly complex that it becomes impossible to trust?
Well, I'm taking the position that this system isn't just an upgrade, it's a necessity. We need what they call a closed-loop infrastructure. By moving intelligence to the edge, literally into the road and the soil, we democratize safety. We're talking about a system that offers the same infrastructure integrity to a military convoy in a war zone as it does to a remote village. It's really all about resilience.
And I'm approaching this with a high degree of skepticism about that very resilience. The engineering is ambitious, sure, but the reliance on agentic intelligence, that's AI that can take action, and integrating notoriously fragile quantum mechanics into the messy real world, well, it poses massive risks. I argue we have to rigorously scrutinize the reliability of any system that claims it can think for itself, especially when human lives are on the line.
Okay, so let's start by just defining what this living ground mesh actually is, because the jargon can get a little dense. I want to strip it right down. In the Tedford vision, the world is covered in these things called nodes.
And when you say nodes, we're not talking about big cell towers.
No. Think smaller. Think ubiquitous. Imagine millions of incredibly smart, ruggedized little walkie-talkies. They're embedded in the asphalt, in the siding of buildings, attached to utility poles, even submerged underwater. And these nodes aren't passive. They're constantly talking to each other, every centimeter of the way.
So on the surface, it sounds like a mesh network. We've seen those before.
It looks like a mesh, but it acts like a brain. That is the key difference. See, traditional infrastructure is passive. A slab of concrete doesn't know when a bridge is vibrating at a dangerous frequency. It doesn't know a car is sliding on ice until the crash has already happened. The Tedford vision inserts a cognitive layer. These nodes use AI to learn from the environment in real time. The whole goal is infrastructure integrity.
Meaning the infrastructure monitors itself?
And self-corrects. And, this is crucial, it's designed for universal access. The documentation makes a really specific point that this isn't just for, smart cities like Singapore or New York. The design is aimed at remote jungles and disaster zones. It's about giving a village with no internet the same safety standards as downtown Manhattan.
That is the humanitarian pitch. And I get it, it's compelling. But I look at the fragility of complex systems. You're describing a planetary brain. In computing, the more complex a system gets, the more attack surface you create, and the more prone it is to spectacular system-wide failure. You mentioned this cognitive layer. That implies agentic intelligence.
Correct. The nodes have agency.
And that is where I get stuck. We're talking about an AI that doesn't just observe, it acts, it makes decisions. And we've all seen how large language models can just make things up, hallucinate with total confidence. How can we possibly trust a distributed AI embedded in the road to make safety-critical decisions, like directing traffic or guiding a vehicle, when we know AI can be so unpredictable?
That is the core anxiety, isn't it? But before we even get to the software, we have to understand the hardware, because the hardware is what makes the software trustworthy. The hero of this whole concept is the Tedford Technologies node.
The smart walkie-talkie?
Let's upgrade that analogy. Think about our current GPS system. Your phone, your car, even a modern tank. They're all basically soldiers just waiting for orders. They look up at the sky, wait for a satellite to tell them where they are, and then they check the cloud to find out where to go. They are totally dependent on headquarters.
And headquarters is very far away?
Exactly. The Tedford node is a scout. It's a self-contained operational unit. It carries its own map, its own compass, and its own brain. If the radio to headquarters, the satellite, or the cloud goes dead, the scout doesn't just freeze, the scout keeps moving.
Okay, but let's be realistic about radio silence. We're not just talking about bad reception in a tunnel. We're seeing a global rise in GPS denial, whether it's malicious jamming in a conflict zone, a solar flare, or just being deep in an urban canyon. When GPS goes dark, most modern tech just fails. What happens to this sophisticated node when the lights go out?
This is where the engineering gets really fascinating. The entire system is built around something they call degraded mode survival, and we need to understand that term. Most systems fail when they degrade. This system just changes tactics.
How?
When the GPS signal is jammed or lost, the node immediately switches to dead reckoning.
Dead reckoning, that's ancient navigation. It's basically guessing where you are based on how fast you are moving from your last known point. But anybody who navigates knows dead reckoning suffers from drift. You make one tiny error now, and in 10 miles, you're completely lost.
In a vacuum, yes. But the node couples dead reckoning with peer signaling. This is the insight. The node doesn't just guess, it asks its neighbors. It pings the node in the guardrail, the node in the pavement, the node on the passing car. It asks, hey, where are you? Okay, if you're there and I'm 5 feet from you, then I must be here.
Ah, so it triangulates its position relative to the local environment, not the global satellite grid.
Precisely. It builds a relative map instantly. And here's the critical detail for safety. The node computes risk locally, in milliseconds. It doesn't need to ask a server across the world for permission to warn a driver. If a kid runs into the street, the node detects it with local sensors and signals the alert immediately. It completely bypasses the cloud.
I will admit that local computation aspect is strong. Reducing latency, the time it takes for a signal to travel, is always better for safety. If the brain is in the streetlight rather than a data center in Virginia, the reaction time is obviously faster.
It's the difference between a reflex and a thought.
However, let's pivot back to the mind of the system. You can have the fastest hardware in the world, but if the software is flawed, you just crash faster. You're talking about AI agents making these calls.
Yes, agentic intelligence.
So we have to address the hallucination problem. If I ask an AI to write a poem and it messes up, it's annoying. If an AI controlling a safety mesh hallucinates an obstacle that isn't there, causing a car to swerve or misses one that is, that's catastrophic. How do we ensure this agent is truthful?
This is where the architectural review by Dr. Eva Marie Mueller-Stoller becomes absolutely vital to the whole project's credibility. Her work on what's called the whiteboard concept is the cornerstone of why this system is considered safe.
The whiteboard. I've seen that mentioned. Okay, break this down for us because it sounds like a classroom.
It is exactly like a classroom. And I want to explain this so a third grader could get it, because it's brilliant in its simplicity. So imagine a classroom with a big whiteboard at the front.
Okay, picturing it.
In this classroom, the AI agent is the student. This student is incredibly smart, very fast, very creative. The student looks at all the data, the traffic, the weather, the car's speed, and runs up to the whiteboard to write down the answer. They suggest a path forward.
But students make mistakes.
Exactly. And that's why there is a teacher in the room. In the Tedford system, the teacher is physics. The teacher is a set of hard-coded rules that simply cannot be broken.
So the AI isn't really in charge?
No, the AI is the proposer. It writes the answer on the board. I think we should turn left at 60 miles per hour. The teacher, physics, looks at that answer and instantly checks it against reality. Nope. At that speed, the tire friction isn't enough. You will slide. The teacher erases the answer before it ever leaves the room.
So the whiteboard is a validation layer. The AI draws up the plan, but the physics engine has to sign off on it before the car actually moves an inch.
Exactly.
Dr. Eva Marie Mueller-Stuhler's review highlights that the AI augments understanding. It finds the hidden patterns, but it never overrides physics. The student can be creative, but the teacher ensures they're always safe.
That sounds good in theory, but reality is messy, Sensors get dirty, glare can blind a camera. What if the AI thinks a red light is green because of a sun flare? The physics of the situation might allow the car to move forward, but the reality is that it's dangerous.
And that's where the safety architecture inside the node kicks in. The system is explicitly architected to do something called refuse false certainty.
Refuse false certainty?
It's a profound shift in AI logic. Usually, an AI tries to guess the best answer, even with bad data. This system is programmed to recognize ambiguity. If the AI analyzes that light and the data is noisy, say the glare is bad, the AI doesn't just guess green. It's programmed to downgrade confidence.
It admits it doesn't know.
It signals uncertainty. It creates a trust-centered framework. If its confidence score drops below a certain threshold, say 90%, it essentially says, I am not sure enough to act. Human, take the wheel. It always prioritizes trust over automation.
I see. So it's designed to hand control back rather than risk a mistake. That's a crucial distinction. It's smart enough to know when it's not smart enough. I can accept that as a safety layer. Okay, but I want to zoom out. We are talking about a planetary brain. And earlier, you dropped a word that usually makes engineers very nervous: quantum.
The AI quantum mesh immigration.
This is where I really struggle with the practicality. We know quantum sensing offers unbelievably precise timing and gravity measurements. That's a fact. But it's also a fact that quantum states are incredibly fragile. Decoherence happens if you look at them wrong. They usually require sub-zero temperatures and vibration-free labs. How on earth do you put a quantum sensor in a device that gets bolted to a highway guardrail or stuck on a Jeep bouncing through the mud?
You're hitting on the biggest engineering hurdle. How do you take the lab out into the wild? And the answer lies in the mesh structure itself. You are right, a single quantum sensor is fragile. If you have one clock and it gets shaken, you lose the time.
Right, it just becomes noise.
But the mesh acts as a stabilizer. Think of it like a crowd of people holding hands. If one person stumbles, they fall down. But if they're linked to 1,000 other people, the crowd holds them up.
So the network compensates for the failure of an individual node.
It's statistical validation. Let's say a quantum sensor in one node detects a tiny anomaly in timing. Alone, that data is suspect. Could be vibration, could be an error, but that node is connected to 1,000 other nodes nearby. This system cross-references that data instantly.
It polls the audience.
Exactly. It asks, did anyone else feel that? If 50 nodes report the same microshift in gravity or timing, the AI says, okay, this is real. If only one node reports it, the AI says, that's a malfunction, ignore it. It turns what was an experimental curiosity, these delicate quantum devices, into operational reliability, just through the law of large numbers.
That actually makes a lot of sense. You're using redundancy to kill the noise. The sheer volume of sensors creates the stability that the individual sensor lacks. But I have to ask about the application. We're seeing Tedford enterprises push this. The documentation talks a lot about contested environments. Is this just a military tool disguised as public infrastructure?
I think it's crucial to be transparent here. The military application is the spearhead. In a war zone, this is a game changer. If satellites are shot down, which is a very real fear in modern warfare, the mesh keeps communications up. That saves soldiers' lives. But the vision described is for humanity.
So how does the military tech help the civilian?
Just apply that same logic to a disaster zone. Think about a remote village in a jungle or a coastal town in a developing nation that gets hit by a Category 5 hurricane.
Right? Usually the cell towers snap, the power goes out, and they're completely dark.
They're cut off from the entire world. But with the living ground mesh, because the nodes are self-contained and self-healing, they maintain that infrastructure integrity. Even if the main power is gone, the nodes, using battery or solar, they continue to talk.
So the rescue teams can still navigate. The village can still broadcast a distress signal.
Precisely. It gives that remote village the same navigation accuracy and safety warnings as a major tech hub. It creates universal access. It flattens the curve of safety inequality. It stops safety from being a luxury product.
I did notice in the files there was a mention of an oceanic extension. This seems like the final frontier of this so-called planetary brain.
It's the piece that truly closes the loop. The mesh doesn't just stop at the shoreline. It extends into the ocean using smart buoys and even seabed nodes.
But physics gets in the way again. Radio waves, Wi-Fi, GPS, cellular, they do not travel through water. You can't use a mesh of radio signals underwater.
Correct. You can't use the same language. That's why the underwater nodes use acoustic networking.
Sound waves.
Whales have been doing it for millions of years. The nodes chirp and sing to each other using coded sound waves to transmit data. They link up to surface buoys that act as gateways, translating the sound back into radio for the air-based mesh. It effectively connects the whole planet, land and sea, into one synchronized system.
I have to admit, the scope is breathtaking. And looking at their letter to Dr. Ava, the focus on acoustic networking and inertial systems for the underwater part shows they aren't just hand-waving away the laws of physics, they're engineering around them.
It's all about using the right tool for the medium. Radio on land, sound in the water, all bound together by this AI cognitive layer.
I think I'm starting to see why you call it a closed loop. You have the quantum sensors providing the raw, hyper-accurate data, you have the meshy net providing the redundancy, the body of the system, and you have the AI acting as the brain to make sense of it all.
And checking it against the teacher of physics.
Right. I'm still not convinced it'll be easy. I mean, the complexity of a planetary brain is a massive risk management challenge. We're talking about billions of lines of code. But the capability, specifically the ability of the Tedford node to work without GPS, that is something we undeniably need. We're far too fragile right now.
It's the difference between a system that fails when things get tough and a system that adapts. We're living in a world where a single satellite error can ground flights and crash markets. The living ground mesh moves us from fragile systems that break to resilient systems that heal themselves.
So as we wrap this up, I want to summarize my position. The technology described here, the ability to maintain degraded mode survival, and the rigorous safety checks Dr. Eva reviewed is groundbreaking. I am particularly impressed by that refusal of false certainty. That's a feature we need in all AI, not just this mesh.
It really does set a new standard.
It does. However, I remain cautious. We're talking about wrapping the entire planet in a digital skin. That requires a level of trust in TL Tedford Enterprises and the system's architecture that has to be earned, not just given. If this mesh fails, the consequences are global.
And that's a fair skepticism. But from my perspective, the fusion of the whiteboard concept, the resilience of the mesh, and the precision of quantum sensors, it's the only way to solve the problem of our current dumb infrastructure. We really can't navigate the 21st century with 20th century roads.
And perhaps that's the transition point we're at, moving from that centralized control, always waiting for the satellite, to a distributed, edge-based intelligence.
I believe it is. The Tedford node represents a shift towards safety that is local, immediate, and truthful.
It is certainly a debate worth having as these technologies leave the lab and start entering our streets.
Absolutely. And we invite you, the listener, to consider this. Are you ready to trust your safety to a living ground mesh?
Thank you for joining us on this deep dive.
Until next time, keep questioning.